Okay, so here are my chapter 3 review videos, and starting with 3.1. So today for 3.1 I'm going to talk about the time rates of change. And basically whenever you have a function, usually the x serves as a function. Usually the x is time, some sort of time, so like x equals hours, or here, let me write this differently. Usually x can be written as hours or seconds, years, days. And then y, the function of x, is usually a distance like miles, feet, people, and height of a plant. And so when we have this, the function itself finds a rate, and that rate can be described as dy over dx, or change in y over change in x. So that would be, so in the case of this first row, that would be miles per hour. Here, case number 2 would be feet per second. Number 3, people per year. And number 4, height per day. So yeah, that's like the basic understanding of this. So say we have this example. A ball is thrown upward and its height at time t is given by h of t equals negative 10x plus 10x plus 20. Find the velocity at any time, initial velocity, and velocity when the ball hits the ground. So basically what we're going to do is find the first derivative of this function right here to give us the velocity, because the first derivative is going to give us the change in x over change in y, or the slope of this function. Oh, sorry, change in y over change in x. Oopsies. Yeah, okay. So that would be the same thing as negative 20x plus 10, which is the velocity at any given time. And then for the initial velocity is when time equals 0. Oh, so instead of x, I should use, oops, I should have made these x's t's up here. That's why this is confusing. So this is a t, and this is a t. Sorry about that. So this would be negative 20t plus 10. And so now when t equals 0 at the initial velocity, or at the initial time, the initial velocity would just be negative 20 times 0 plus 10, which is 10. And then the velocity when the ball hits the ground is basically when h of t equals 0, or when height equals 0. And so what we have to do is we just have to factor h of t. So we have negative 10x squared plus 10x plus 20, which factors to, let's see, x plus 2 times x minus 1, I believe, 10 times that. 10 times negative x factoring is going to take me a while, hold on. Yes. Okay, 1 second. Okay, this would actually be an x plus 1. Sorry about that. Okay. So yeah, that is pretty much all there is to number 1. Oh wait, sorry, I have to finish this. So we know that it can't be x equals -1 because that's a negative time and that doesn't exist. So I keep using x, but it should be t equals 2. So at 2 seconds the ball hits the ground. So to define the velocity, when the ball hits the ground, we just have to plug in t equals 2 to that first derivative. So -20 times 2 plus 10 equals -30. So yeah, that is 3.1. And now we're going to move on to 3.2. Okay, so 3.2 is about general rates of change. And basically, this is when your x value is not necessarily time. So, say we have the problem here. The total cost of running a train from Paris to Marseille is given, is given by C of V equals 1/5 V squared plus 200,000 over V euros, where V is the average speed of the train in kilometers per hour. So, for part A, find the total cost of the journey if the average speed is 50 kilometers per hour. So, for this, we would just plug in 50 for V in the equation. So, we have A 1/5 times 50 squared plus 200,000 over 50, which would be 500 plus 4,000 or 4,500. And then for part B, find the rate of change in the cost of running the train at speeds of 30 kilometers per hour. So the rate of change would require us to find the first derivative of C of V. So the first derivative, or first let's rewrite C of V because we have a fraction here. So C of V can also be written as 1/5 V squared plus 200,000 V to the -1. So the first derivative of that would just be 2/5 V minus 200,000 V to the -2. And so to find the rate of change at the speed of 30 kilometers per hour, we plug in 30 for V in this first derivative. So C prime of 30 equals 2/5 times 30 minus 200,000 times basically 1/30 squared. So let me calculate this. So once you calculate this, you get 12 minus about 222.22, which is about -210.22. And basically what this is saying is that the rate of change is a decrease of 210.22, decrease at a rate of 210.22 kilometers per hour. And then for part C, I guess I'll have to move this on to another slide, but at what speed will the cost be a minimum? So let's move on to the news. When a cost is minimum, that means that the first derivative is equal to 0. So if we remember, our first derivative was 2 over 5v minus 200,000 v to the negative 2. So I'm going to set this right side equal to 0, and I'm going to rewrite the v to the negative 2 as a fraction. So 2 over 5 times v minus 200,000 over v squared equals 0. And so now I'm going to solve this. I can multiply the whole thing by v squared to get rid of that denominator. So 2 over 5 v cubed minus 200,000 equals 0. 2 over 2 over 5 v cubed equals 200,000. V cubed equals 500,000. And the cube root, and v equals the cube root of 500,000, which is about 79.4 kilometers per hour. So that would be your speed at which the cost is at a minimum. And that is 3.2. Okay, so for 3.3, we're going to be talking about motion in a straight line. So typically with motion in a straight line, you'll find a function that represents the position of an object on an x-axis after time. So in this case, my function would be s of t, and t would be my time. And so if I kind of drew like a position time graph, at time equals 0, or at any time where t is greater than 0, where the position is greater than 0, so s of t is over here. What I'm trying to say is whenever s of t is greater than 0, the object is going to be on the right side of the position 0. And then if s of t is less than 0, then it's going to be, on the left side, because it's negative. Pretty self-explanatory. And the difference between and so oftentimes we'll have to find the velocity using these types of functions, and so we have to distinguish the difference between average velocity and instantaneous velocity. Average velocity, say from maybe time 1 to time 2, would be the same thing as s of time 2, or the function of it. Okay, s of time 2 minus s of time 1 over time 2 minus time 1. So, yeah, that is your average velocity. And then if you're looking at instantaneous velocity from time at like a specific point in time, say time 1, then you would use the first derivative of time 1 to find that value, which would be the same thing as velocity times time 1. Oh, and here the s's are describing displacement, or otherwise known as position. So here, for the average velocity, you're taking the position at time 2 minus the position at time 1 divided by the overall change in time. And then for the instantaneous, you're just finding the slope at the position at the at the position at time equals 1, which would be using the first derivative, if that makes sense. And so in the same sense, to find average acceleration, you would use pretty much the same formula. I'm going to use A for acceleration. So say average acceleration from time 1 to time 2. You would use the same formula, except instead of using the position at time equals 1 and time equals 2 in your numerator, you would use the velocity at time equals 1 and the velocity at time equals 2. And you still divide it by time 2 minus time 1. And basically final time minus initial time. And then the instantaneous acceleration is also pretty much the same thing. Say at time 1, you would just find the first derivative of the velocity at time 1. And that would be the same thing as multiplying the acceleration times time 1. You could also write this as the second derivative of the position function. Okay, so I realized that I think I actually told you guys the wrong equations for average velocity and average acceleration. It's actually where velocity of time 2, the final time, minus velocity of time 1. And the same thing for position. It would be final position, or position at time 2 minus position at time 1 divided by time 2 minus time 1. So I have this new problem right here. And so to find the average velocity, I would do the position at time 2 minus position at time 1 divided by time 2 minus time 1. So that would be, let's see, when time equals 2 in this function, we get time equals 5 first. We get 5 minus 50, so negative 45. And then minus 5 minus 8, which is negative 3. So minus negative 8 or minus negative 3, or the same thing as plus 3. And then we divide it by 5 minus 2. So that gives us negative 42 over 3, which is negative 14, or a decrease by 14 centimeters per second. Okay, so I don't know what happened here. But anyways, if I use these same numbers and I actually want to find use the same function and I want to find the instantaneous velocity at, say, time equals 2, then what I would do is I would take the derivative of s of t, which is just negative 4t, and I would plug in whatever time I'm looking at. So if I said I wanted to find the instantaneous velocity at time equals 2, I'd say first derivative 2 equals negative 4 times 2, which is just negative 8 centimeters per second. So that's not too bad. Okay, so for 3.4, we're going to go over some curve properties. So say I have the function negative, let's see, hold on, where's my pen? Okay, negative x cubed plus 3x squared plus 5. And I want to know over which intervals the is the function so over which intervals are the function increasing, and over which intervals is the function decreasing. So if I look at a picture of the graph, it kind of looks like this. Okay, and so basically, if I find how do I know when it's increasing or decreasing? I'm going to look at the rate of change, right? So that would be change in y over change in x, which is the same thing as the first derivative of this equation right here. So that would be negative 3x squared plus 6x. Okay. And so how do I know when it so I know that it, like, if I look at this graph here, I know that it's decreasing up until it hits this vertex right here. And then I know it's increasing up until it hits this vertex right here, and then it decreases again. So what I'm going to do is I need to find these points right here in order to know what the intervals are for when it's increasing and decreasing. And how I find those is by setting the first derivative equal to 0. Okay, so if I say negative 3x squared plus 6x equals 0, I can factor out a negative x, and I'll get 3x minus 2 equals 0. So x equals 0 or 2/3. So these are my x coordinates for these 2 points up here, right? And so now I can plug these x coordinates back into the original equation to find the y coordinates. So for x equals 0, I can plug it in, so negative 0 cubed plus 3 times 0 squared plus 5, which is just 5. So this coordinate right here is 0, 5. And then if x equals 2/3, I would say negative 2/3 cubed. Now this is kind of a gross number. That's okay. Plus 3 times 2/3 squared plus 5. Oh, you know what? I realized we don't actually need the y's. We only need to know the x values. So you can pretty much just ignore this. But if you were going to continue and find the points of inflection, that's what you would do. But if we just ignore this for now, we can say that it is increasing at the intervals at the interval 0 to 2/3, right, which is right here. And then we can say it's decreasing at the intervals, well, here it would just be like negative infinity to 0, and then so negative infinity to 0, and then right here would be 2/3 to infinity. If they had made this graph over a certain interval, say like -5 to +5, then instead of the infinities here, I would have -5 and +5. Just FYI. Okay, so I erased this little area over here on the right just to make another point. Basically, if we look at a sign change, like number line, I guess, I don't really know what to call this, and we write down our what would be these? Write down our when the function is when the first derivative is equal to 0. We can see that on the left side of the 0, all of the or the slope of the line is negative. In between 0 and 2/3, it's positive, and then after 2/3, it's negative again. This just reinforces the idea that of like when it's increasing or decreasing. Sorry, I don't know why I drew that. So because from negative infinity to 0, it's decreasing. That's why the slope is negative here. Or that's why, that's also why the first derivative of the equation would be negative as well. And so because because the signs change before and after 0 and before and after 2/3, we know that 0 and 2/3 are points of inflection, or sorry, are the minimum and maximum. So here before and after 0, we see that it changes from a negative slope to a positive slope. So it goes down and then back up. So that means 0 is a minimum. And then at 2/3, it goes from having a positive slope to having a negative slope. So 2/3 is a max. As you can see, whenever there's a concave up, that indicates that there's a minimum, and when there's concave down, that indicates there's a maximum. And then for points of inflection, that's basically when, okay, I don't have an example here, but for points of inflection, if, say, for these numbers, instead of this being positive and this being negative, let's say they were both positive. That would mean that there's a point of inflection because it doesn't change direction. There's a tangent line at that point. However, the function itself doesn't change direction. Therefore, there's a point of inflection. Okay, so for 3.5, we're going to be talking about rational functions. Okay, so just some things to note. Vertical asymptotes can be found by solving h of x equals 0. Horizontal asymptotes can be solved by finding what value f of x approaches as the absolute value of x approaches infinity. And oblique asymptotes are neither horizontal nor vertical asymptotes, but they can be found using the division process, and then finding what the function f of x approaches as the absolute value of x approaches infinity. So there are pretty much 3 types of functions that we can focus on here. The first one would be linear over quadratic. Second one would be quadratic over quadratic. And the third would be quadratic over linear. And so I'm going to find examples of both, and all 3, and I'll be right back. Okay, so here are some problems, and I already started working on the very first example. So if I have the equation y equals 2x over x squared minus 4, I know that I have a vertical asymptote at x equals plus or minus 2 because I set my denominator equal to 0 to find that. And then I know I have a horizontal, or for vertical asymptotes, that's when y or x is equal to, actually, okay, never mind, scratch that. Yeah, anyway, so for horizontal asymptote, I know that my horizontal asymptote's at y equals 0, so I found those two. And then I found the first derivative of y, which is seen here. And then using that, I plotted my points for my vertical asymptote, and I also plotted a 0 here because that's where I have a stationary point, or a a point of inflection, a point of inflection. And so if I continue with this and I use sign analysis, then I will realize that on the left side of -2, when I plug this into my derivative, which simplifies to -2x squared minus 8 over the bottom, which is positive for sure, then I get that it becomes increasingly negative as it approaches -2. And then between -2 and 0, I see that it, say like -1, it's also negative, or decreasing. And then between 0 and 2, it's also decreasing. And then between 2 and infinity, it's still decreasing because the numerator is actually always negative. So I have asymptotes here, and the graph actually looks something like this. So yeah. Okay, and this app is kind of messing with me and it's making my things look all weird, but anyways, using the same method, I can also solve these, and I'm just going to draw the graphs because the methodology is pretty much the same. So if you guys want to try this and you want to check your answers, I believe this one's probably like that. Yeah. Okay. Moving on. 3.6, inflections and shape. Okay, so let's just take a moment to observe the shape of a curve. So if a curve is like this, and it's like a smiley face, it says concave up. And that is basically when the second derivative of, sorry, I don't know what happened, but so when the second derivative of x is greater than 0. And the point of an inflection is where this second derivative equals 0 and it changes sign. And yeah, okay. If it's concave down like this, like a frowny face, then the second derivative of x is less than 0. And when we refer to the point of inflection, there are two different types. There's horizontal or stationary, or non-horizontal and non-stationary. And basically, you have a horizontal inflection point when the tangent is a horizontal line, and when the tangent is not a horizontal, say it's like this, then that is when you have a non-horizontal or non-stationary inflection point. And the way you know this is if the second derivative of x is equal to 0, that means it is horizontal or stationary. And stationary. And if it is not equal to 0, say it's greater or less than 0, then that means you have a non-horizontal or non-stationary point of inflection. Okay, so we're on to the very last section, 3.7. This is about optimization. Okay, so here I have an example of what problem using optimization would look like. So basically there are 4 steps. First you have to draw a large clear diagram of the situation. Then you need to construct a formula with a variable to be optimized, so basically maximized or minimized, and it needs to be written in terms of one variable, such as x. Then, for the third step, you have to set the first derivative equal to 0 and solve for x. And finally, use a sign diagram or the second derivative to show if you have a minimum or if you have a maximum. And so for step 1 of this problem, I have a box and I'm finding the length of each side. Then I use the volume by multiplying length, width, and depth, and I notice that x is greater than 0 and 25 minus 2x is greater than 0, so therefore x has to be between 0 and 12.5. Then in step 3, sorry, I'm trying to turn this in by midnight. I really want to get these bonus points. Okay. Basically, in step 2, the point of this part right here is to set a restriction and make sure that, because my x can only be up to a certain length, I cannot, because if it's greater than 12.5, then my side, the length of my side becomes negative, and that's not possible. Okay, now I go to step 3, which is to find the first derivative of my equation. And so here's all the work, and when I set that equal to 0, x equals 5. And I know that when I set my first derivative equal to 0, that shows either a maximum or a minimum, or a point of inflection. And so, using the sign diagram, or using the second derivative, either way, I can see that before reaching 5, from 0 to 5, I get a positive number when I plug in 5 in my first derivative. I get a positive, and in my second derivative I get and in my first derivative after 5 I get a negative number. I can also use the second derivative test and show that and because I end up with a negative 40, which is less than 0, I know that the shape of my function is concave down, and that I have a local maximum. That is the second way, but the first way was just to make a sign diagram of the first derivative, and I know that I have a slope that's increasing and then decreasing. Therefore, it's concave down, and using the same logic, I have a local maximum. And as you can see here, I have a local maximum, or a maximum volume, at x equals 5. So when and that x equals 5 when 5 centimeter squares are cut from each corner. And that is 3.7. Yay, finally done. Now I have to turn this in.